Welcome to Chemistry Goes to the Movies. This time we'll be discussing invisible inks, particularly disappearing inks. The Miranda's map from Harry Potter features disappearing ink. When Harry taps the map and says, "I summon this rhyme up to no good," the writing on the pattern appears. However, when he says "mystery," the writing disappears again. Disappearing inks aren't so magical, but there is an important science behind it. A disappearing ink is made up of a mixture of a water-based indicator and a basic solution. For example, phenolphthalein and sodium hydroxide. This solution appears to be pink in basic conditions at pH 10, and colourless in neutral and acidic conditions at pH 7 and below. This means that the mixture of phenolphthalein and sodium hydroxide is pink in colour. However, the water present in the indicator reacts with carbon dioxide in the atmosphere to form carbonic acid. The carbonic acid then reacts with the NaOH to neutralise it, so the solution therefore turns colourless, so the writing on the paper will disappear. When another base is added, for example ammonia, the solution will turn pink again as the pH has increased, so above pH 10. Phenolphthalein acts as a weak acid, and the equilibrium equation for this acid can be created. This shows that when acid is added to the solution, the position at the equilibrium will shift to the left to the reactant, so the solution will appear colourless. However, when a base is added, the position at equilibrium will shift to the right to the product, so the solution will appear pink. Other indicators also work in a similar way. For example, litmus and methyl orange, as shown in the table. The effective pH ranges for the indicators are shown in the table. These pHs depend on the P indicator of the indicator. The acidification equation, similar to phenolphthalein, can be expressed in terms of K indicator equals the concentration of hydroxide ions times concentration of ion divided by the concentration of indicator. At the halfway point between the colour changed indicator, acid and the ion will have equal concentrations. Therefore, K indicator is equal to the concentration of H. This means that the pK indicator equals the pH of the indicator solution. Therefore, the pK indicator value for phenolphthalein is 9.3, and the pH range of the indicator is 8.3 to 10. This range is due to the colour change to indicate. There are several other types of invisible ink. For example, acids and bases with an indicator are similar to disappearing ink, but the remaining will remain visible as the reaction is irreversible. An acid can be used as an ink, and an indicator will be used to view it. However, it could be used the other way around. A coloured indicator could be used to ink, and an acid in the base, or a base, could be used to view the writing. For example, again, the phenolphthalein and sodium hydroxide. These type inks are probably the most simplest to make, as lemon juice, for example, contains citric acid, which is a weak acid. The citric acid will oxygenate the paper. Therefore, when the paper is heated, the area of phenol is oxidized and appears brown in colour. There is also fluorescent inks, which appear under UV light. Laundry detergents with optical brighteners, sunscreens and soap can all be used as fluorescent inks. Their uses can be seen in many films, and are also used as security on documents such as passports and banknotes. The fluorescent inks work by absorbing electromagnetic radiation. They are excited by this, and their electrons jump to higher energy values. However, when the electrons jump back down to their ground states, they emit UV light. So as chemistry goes to the movies, invisible inks. Thank you for watching.